All right, today we are diving deep into one of the most fascinating and frankly, mind-bending fields in all of technology, quantum computing. We're going to peel back the layers of this thing all the way from the super strange physics to the very real career opportunities that this revolution is already creating. You know, quantum mechanics is weird. So weird, in fact, that even the great Albert Einstein was totally baffled by it. He famously called quantum entanglement spooky action at a distance. And he was trying to describe this bizarre, almost magical connection between particles that are somehow linked, no matter how much space is between them. And that is the perfect question, right? How do we jump from this abstract idea that puzzled Einstein himself to a whole new generation of unbelievably powerful computers? Well, as it turns out, that spooky behavior is the very thing that gives these machines their incredible power.
So to really get a handle on that potential, we first have to look past the way normal computers work. It's time to go beyond the binary and really understand the quantum leap.
Okay, so think about it like this. Your laptop, your phone, they all use bits. They're basically tiny light switches. They can either be on or off, a 1 or a 0. Simple. A quantum computer, on the other hand, uses something called a qubit. Now, a qubit is way more like a dimmer switch. It can be a 0, it can be a 1, or, and here's the crazy part, it can be both at the exact same time.
That dimmer switch effect? It has a name, superposition. And here's the real aha moment. Because a single qubit can hold so much more information than a classical bit, a quantum computer's power grows exponentially with every single qubit you add. That's where this massive, almost unimaginable computational advantage comes from.
And then you've got the other piece of this incredible puzzle, entanglement. This is Einstein's spooky action, but applied to computing. When you entangle qubits, their fates become intertwined. What happens to one instantly, and I mean instantly, affects the other, even if they're miles apart. This lets you do these incredibly complex, coordinated calculations that are just flat out impossible for any classical computer. Okay, so we've got these incredible, kind of weird new building blocks. But how do you actually use them? How do you take all this weirdness and build something you can actually program?
You know, it might sound super abstract, but the process is actually surprisingly familiar, especially if you've ever coded before. First, you define your qubits. Those are your units of information. Then, you apply what are called quantum gates, which are just basic operations that mess with the state of the qubits. You string these gates together to build a quantum circuit. That's your algorithm. And then finally, you hit run, either on a simulator or on real quantum hardware.
So what you're looking at here is a super simple example of what that circuit might look like. Those two lines are our qubits. The H is a gate that puts a qubit into superposition. That at and X combo is what entangles them together. And the M at the end, that's you measuring the final result. It's basically just a set of instructions for the quantum computer to follow.
And this isn't just theory, by the way. People are out there right now building these circuits with real-world tools. You've got big names like IBM with its Qiskit framework and Google with Cirq. And then there are libraries like PennyLane, which are really pushing the envelope on quantum AI.
Speaking of which, one of the absolute most exciting areas where all this is coming together is in the world of machine learning. This is where things get really, really powerful.
Yep, a whole new field is popping up right at this intersection. It's called quantum machine learning, or QML for short. Researchers are developing algorithms that could totally supercharge AI, helping us tackle huge problems in finance, medicine, you name it. Problems at a scale we've just never been able to handle before.
And of course, this creates a brand new, super specialized job, the quantum machine learning engineer. I mean, these are the experts who are literally building the bridge between these two revolutionary technologies. They're designing the quantum neural networks of the future.
So what does it actually take to become a QML engineer? Well, it's a really fascinating mix of skills. You've got to be good with those quantum frameworks like Qiskit and Cirq, and you need to have strong Python skills. But you also need a really deep understanding of linear algebra. That's the math behind it all. And of course, you need to be an expert in classical machine learning too. It's a true hybrid role.
And trust me, that kind of hybrid expertise, it is in crazy high demand. This isn't just some fun academic exercise anymore. This is a rapidly growing job market with very real, very high-value careers. Let's just talk numbers for a second, because they're pretty impressive. You're looking at a quantum research scientist pulling in up to $226,000 a year. Even a quantum engineer can easily expect a six-figure salary right out of the gate.
And yeah, at the very top end, a senior quantum algorithm scientist can be making up to $273,000. The point is, learning to master all this spooky physics can lead to some very, very tangible rewards.
So, with all this incredible potential and these amazing jobs, are we basically on the verge of the next great technological revolution? Well, the answer is kinda yes, but also not quite yet. See, we're currently in what experts call the NISQ era. That stands for Noisy Intermediate Scale Quantum. What that really means is that today's quantum computers are powerful. For sure, they can already do things classical computers can't. But they're still pretty small and super sensitive to making errors or noise from the world around them. We're just not at the point of building these perfect, flawless machines yet.
But, and this is a big but, the progress here is unbelievably fast. Every single day, researchers are figuring out better ways to correct errors and build more stable qubits. So, the big question remains, are we on the cusp of solving some of humanity's most unsolvable problems? The honest answer is we're just at the very beginning, and the true impact is still out there, waiting to be discovered.